Welcome gamers and everyone else to gamers and everyone else's guide to school, AP Chemistry Cram, where I'm going to be trying to cover some of the more difficult and important topics in the AP Chemistry test, since by the time this goes up, it's going to be tomorrow, and tomorrow's in 3 hours. The test itself is probably in like 12. So this episode is going to be about chemical reactions, and we will cover as much as possible that is going to be on the test relating to chemical reactions, including like the types of chemical reactions, balancing them, stoichiometry, and certain analysis. So the main types of chemical reactions you'll see on the AP test are synthesis reactions, decomposition reactions, acid-base reactions, oxidation-reduction reactions, combustion reactions, and precipitation reactions. So let's just define these and give an example real quick. So a synthesis reaction is a reaction where elements or simple compounds combine to make one single, more complicated compound. A decomposition reaction is literally the exact opposite. It's one in which a single compound is split into one or more simple compounds or elements. An acid-base reaction is pretty self-explanatory. You'll probably see a Bronsted-Lowry version, in which a acid or proton donor that carries an H+ ion and a base or proton acceptor, which will carry an OH- ion, which is a proton acceptor. Well, together they'll react, and then they'll make a salt and water with the H+ from the acid and the OH- from the base. So an oxidation-reduction or redox reaction is a reaction that involves transferring of electrons and then reducing oxidation number and charge. Combustion reaction in the scope of the AP test involves a hydrocarbon reacting with oxygen to form carbon dioxide and water. A precipitation reaction is one in which the solubility rules are taken into account to see whether or not a precipitate will form from a solution of otherwise aqueous compounds. So now we're going to go through the more complicated parts of chemical reactions. So the most basic problems you'll get involve literally just balancing them. So for example, let's go through the combustion of methane. So methane is CH4, and the combustion is combining it with oxygen gas to make carbon dioxide gas and water. So the easiest way to balance an equation is to just count. So on this side, there's 1 carbon, 4 hydrogens, and 2 oxygens. And then on the product side, there's also 1 carbon, there's 2 hydrogens now, and there are 3 oxygens. So the first thing that I would do is see that you need hydrogens on this side, on the product side. So if you add a 2 to that water right there, then you'll now have 4 hydrogens, and you'll now have 4 oxygens. So now you can see that you're missing oxygens on the reactant side. So now you just added 2 right here as well, and now you have 4 oxygens, and your equation is balanced. It's really simple to do it this way because the law of conservation of matter says you can't just lose any atoms. So counting them and then adding coefficients to make sure that you're keeping the law of conservation of matter intact is generally going to be pretty easy. So we're only going to do one example of this, even though you might have more in the multiple choice section, where it's like if we wanted to use the same problem, or actually let's make hydrogen peroxide with this. So you could have a question that says, what is the coefficient on oxygen gas? So this is obviously not balanced because there's 3 oxygens versus 2, and then there's 2 hydrogens. So if you want to write that, you can just write it. versus on this side you have 2 of each. So obviously if you want more oxygens, you're going to have to put a 2 there. And now you have 4 of each on this side. So now you have to actually put a 2 here. And now you have 4. And now you have 4. So if it said what is the coefficient on oxygen gas, you just say 1, because that's what the coefficient on oxygen gas is. So yeah, we're not going to go through balancing too much. I'm just going to make it necessary on all the future examples, since that's something you should probably do anyways. So for now, we're just going to move on to stoichiometry. So I'm going to use the example of potassium chlorate, so KClO3, and then it's decomposing into KCl and oxygen gas. So let's go ahead and just write out everything real quick. So there's 1 potassium to 1 potassium, and then 1 chlorine to 1 chlorine, and then here's the discrepancy, 3 oxygen versus 2 oxygen. So here's something you can do. You can just add a 2 here, like just go up by 1, but you can't ever get 4 with a multiple of 3. So if you just put a 3 here, then you'll get 6, and then it's easy to get 6 with that. You just put a 2 here, then you get 6, and now these also become 2, and then you're gonna have to put a 2 here, and then those also become 2, and you're balanced now. So that's pretty easy. So now we're gonna say, for example, that you were given 12.55 grams of KClO3, and we want to figure out how much how many grams of oxygen would be produced. So in order to do this, you're going to have to go through dimensional analysis. So let's go ahead and just erase. Ooh, that is not what I wanted. So we're going to go ahead and erase real quick all of that balancing stuff, and we're going to go through and see. So if you have 12.55 grams of KClO3, so you can go ahead and look on a periodic table to find the molar mass. The molar mass is 122.55 grams per mole. So this is a way that my chemistry teacher taught me to do dimensional analysis, because it's a lot easier to cancel out. So the grams of KClO3 cancel with the grams of KCl3, and then you have 1 mole of KClO3. So now the coefficients in a chemical equation actually mean the mole ratios that are used. So 2 moles of KClO3 will actually result in 2 moles of potassium chloride and 3 moles of oxygen gas. So if this is 1 mole of potassium chloride per that many grams, then you just put 2 moles here. I'm not going to write out the actual compound because we don't have enough space, but you guys definitely should. It'll make canceling much more safe. Like, I can't cancel this with this because it's not the same. This is KClO3 and this is oxygen. So 1 mole of O2 gas weighs, I believe, let me check real quick. Yeah, 32.00 grams. So 32.00 grams. So now if you plug that all into your calculator, so you just multiply everything on top, divide everything on bottom, then you are actually going to get how many grams of oxygen gas were consumed. So plug that into a calculator real quick. That's 32.00 is equal to that. So then you divide by 2, and then you divide by 122.55. and then you get that 4.915 grams of oxygen gas were produced. So that's how you do stoichiometry using a balanced chemical equation. You just go from grams to moles, and then you use the moles that are given to you in the balanced chemical equation with coefficients, and then to find the moles of whatever you want, and then you can go back from moles of something to grams of something using molar mass again. So now that that's out of the way, we can, so I'm only gonna do this one example. I can make and upload more problems if you guys want to see this, but this is generally pretty simple for people who are taking AP chemistry. So now we're gonna move on to combustion analysis. So combustion analysis is pretty much the same thing. You can see that when a hydrocarbon fuel is burned, from like the previous few slides, this one, that it always produces carbon dioxide and water. So using that, if you figure out, if you are given how many grams of carbon dioxide and how many grams of water were formed, you get to figure out the empirical formula of the hydrocarbon that was burned, and even if you have the molar mass of the hydrocarbon, then you can actually figure out the molecular formula. But according to the course and exam description, that's actually beyond the scope of the course. So let's actually start just with an example of, so you are given that 88.02 grams of carbon dioxide were produced. So 88.02 grams of CO2. So, and then you were also given that 45.05 grams of water were produced. 45.05 grams of water. So now, using the same dimensional analysis, so this is actually going to be moles on top here because you have to cancel with the grams on the bottom. So the molar mass of carbon dioxide, which is 44.01, you can see that this is actually just going to be 2 moles of CO2 is what you're going to actually get here. So let's go ahead and erase that, and probably not going to need that much space there either. So that's equal to 2 moles of carbon dioxide. So because, let me do the water first. So the molar mass of water is 18.02 grams of H2O per 1 mole of water. So again, so grams cancel with grams of CO2, grams of H2O cancel with grams of H2O, and through this, you should get 2.5 moles of water. So now, so in any, so the moles of carbon dioxide is equal to the moles of carbon that were released, and again, with the law of conservation of mass, you can't lose anything, so you know that it's actually the same. So you know that on the reactant side there were 2 moles of carbon, and because the only thing on the reactant side is oxygen and the hydrocarbon, that there's 2 moles of carbon in the hydrocarbon. And now, so moles of H2O, so in this case it's 2.5, that's every 2 moles of hydrogen, and the only source of hydrogen on the reactant side again is the hydrocarbon. So you're actually going to have 5 moles of hydrogen. So the formula, empirical formula for the hydrocarbon that you burned was C2H5. And then if you were given the molar mass, you'd be able to find the molecular formula, but that's beyond the scope of the exam. So now we're going to do a quick lesson about enthalpy, because I know the methods behind enthalpy confuse a lot of people. So the basic formula is enthalpy of the reaction is equal to enthalpy of the products minus enthalpy of the reactants. So if the enthalpy of the reaction is positive, the reaction is endothermic, so it took in heat. And then if the reaction, or enthalpy of the reaction is negative, the reaction is exothermic, so it gave off heat, such as like combustion. So that is because when you break bonds, you absorb energy, because energy is needed to split the bonds apart. That's why energy is also needed to go from like a solid state to a gaseous state, because they're really clumped together in a solid state versus in a gaseous state they're really like loose from each other. So for example, a bond broken would be in a decomposition reaction, and then a bond formed would be in a synthesis reaction, and that has a release of energy. So yeah. So again, with the exo and endothermic, if it's endothermic, heat was taken in, exothermic, heat was released into the surroundings. So now we're going to go back to acid-base reactions real quick. So we're going to actually switch back to my drawing tablet here. So, okay, the recording's still going. Okay, sorry. So it's pretty basic about, so let's actually go back to the acid base. So here, so you have hydrochloric acid and then sodium hydroxate. And then, so the salt formed is always going to be the anion from the acid and the cation from the base, because the hydrogen from the acid and then the OH minus from the base must combine to make water, always. So then the only two things you're left with are the cation and the anion from the acid and the base. So that's always going to be what the salt is. So now moving on to oxidation rules. So these are for redox reactions. And let's just go over the basic rules for the assigning oxidation numbers to atoms. So any non-bonded neutral atom has an oxidation number of 0. Any ion has an oxidation number equal to the charge of the ion itself. Oxygen in most compounds has an oxidation number of -2, which it usually ionizes into. It's only going to be -1 if it's in a peroxide. Likewise, hydrogen is pretty much always +1, like its ion, unless it's bonded to a metal, then the oxidation number is -1. And then in the presence of no oxygen, the most electronegative element, like fluorine, will follow the oxidation number for its most common ion. Again, fluorine, it would be -1. And now the most important one is that bottom one there. It says the oxidation number is of a compound, like of all the atoms in a compound, must add up to its charge. So in a neutral compound, the oxidation numbers must add up to 0, because that's what the charge would be. So using these in combination with a redox reaction helps you see which reactants were oxidized and which were reduced as part of the reduction part, which is lowering the oxidation number, lowering the charge, which is also adding an electron, because electrons are negative, so you're going to reduce the charge if you add one. So redox reactions are also used in electrochemistry, but that is not something I've actually taken in college yet, so I wouldn't really feel comfortable explaining it to you. So we're going to go into redox equations as an example. So an example of a redox reaction is one that I have given back here. Yeah, so it'd be Cl2, so chlorine plus potassium iodide goes into potassium chloride and iodine. So this is not balanced. So there's 2 chlorines here, 1 potassium and 1 iodine, versus on this side there's 1 potassium, 1 chlorine, and 2 iodine. So in order to get 2 iodines / 2 chlorines, you need to put a 2 here and then a 2 here, which will in turn also fix the potassium on each of these. So now it's time to go look into actually looking at the oxidation numbers of these. So again, chlorine is non-bonded, it's neutral, so the oxidation number is going to be 0. And then on this side, iodine, oxidation number is 0, non-bonded, neutral. And then, so the most electronegative atom, so as we can see back from here, so without oxygen, the most electronegative atom will have its ions charge. So switching back to this, you can see that. So the most electronegative atom in this case is chlorine, so the ion on chlorine is almost always -1. Iodine is almost always -1. So that means potassium, in order to keep that compound neutral, must have a +1 charge, which if you were to look at a periodic table, that would also its most common ion. So the next thing you have to worry about for redox reactions is actually half reactions. So there's two parts of a half reaction, thus it being called a half reaction, and that is the reduction part and the oxidation part. So we're gonna have the reduction part up here and the oxidation part down here. So as far as a reduction goes, remember I said reduction in charge, reduction in oxidation number. So chlorine actually starts at 0, and then on the product side, it's actually 2 Cl minus ions. So that's actually a -1 because they have to be minus. So what do you have to do to balance out like the charges and the oxidation numbers in this part of the equation? Is you're actually going to have to add 2 electrons here, because electrons are what do the actual reducing. So because you added these 2 electrons here and you don't see them show up here, you have to be able to cancel them out in the actual oxidation half. So as you can see, the potassium stays the same with +1, so that's actually not going to be a factor. It's a spectator ion. So the only option we have left is iodine, which is 2I minus on this side, bonded to the potassium, and it's going to go into iodine 2. Or sorry, just iodine. So it's got 0 oxidation number versus -1 oxidation number. So again, to balance out the charges, you're going to have to add 2 electrons here to balance it out. So now these electrons will actually cancel with these electrons, and that's how you know that your redox reaction problem was actually, the half reactions were actually done correctly. So yeah, so we can now switch on, continue to, actually no, sorry, let me go over this real quick. So there are redox titrations as well as acid-base titrations, which are called neutralization reactions, but they are usually complicated mathematically and conceptually, and they require like a lesson on titration curves, but we don't have time for that because this video is already going to be pretty long and you guys should probably get some rest. So for the final type of reactions that we have yet to cover, it's the precipitation reactions. So the only thing that really matters with precipitation reactions is knowing the solubility rules. So I only have 2 listed because those are the only 2 that the Princeton Review says you need to know, but I think you should know more of them, and I'll leave a link in the description below to a resource that has all of them. But the 2 that the Princeton Review says are the important ones are anything with an alkali, so group 1, or ammonium, so NH4+, cation is always soluble. That 4 should be subscripted, so it's NH4+. The exceptions to that would be some certain lithium salts, and then anything with a nitrate anion, so NO3-, are always soluble. So this is pretty much only used in net ionic equations, so on the next page. So for example, so this is a precipitation reaction where it's cadmium sulfate and potassium sulfide. will react together to make cadmium sulfide and potassium sulfate, but cadmium sulfide is insoluble with the solubility rules. So if you wanted to do a net ionic equation, you just write out everything that's aqueous as its own ion, because that's really what it is. It's dissolved, and it's not really binded together, even though it technically is written that way. So, except on the product side, so the cadmium sulfide on the product side is actually written together because it's solid. It's not aqueous. It's not dissolved. So then when you eliminate the things that are the same, so that the 2 potassium plus ions on the product and the reactant side, so here and here, you can cross that out, and you can cross out the sulfate, so cross that out, because those don't actually change, they stay aqueous the whole time. So the only thing that actually changes and precipitates is the cadmium ion here, the sulfide ion here, and it becomes cadmium sulfide. So that should be about it. Sorry we don't have enough time to go over titrations, but the test is tomorrow. You guys should get some rest. And there are, in my personal opinion, more important things to know, because those titrations might cover like a few questions, like especially graphs. You probably study that. But titration problems themselves would have to be pretty much a free response because of how mathematically intensive they are. So I don't think that's necessarily super important. But yeah, so as always, if you like the video, please be sure to leave a like and subscribe. If you disliked the video or thought it confused you, be sure to leave a comment with some constructive criticism. For now, this will about do. This has been String from GG to School, and peace.